Hi, I'm Mark Barsamian. In this video, I'll be discussing an introduction to functions and properties of functions. I'll actually start by discussing relations some more. I'll introduce what are called relations from one set to another set, and then we'll begin our discussion of functions. And then finally, I'll discuss properties of functions, surjective, injective, and bijective properties. This material is from section 1.3 of our book, more specifically just pages 9 through 12. These 6 homework exercises are relevant to this video. As I mentioned, we'll start by discussing relations some more. We'll be talking about what are called relations from one set to another set. This concept is not discussed in our book, section 1.3, but it is a useful concept that will help clarify the concepts that are discussed in our book. So, to start with, recall the definition of binary relation on a set from section 1.2. To say that R is a binary relation on a set S means simply that R is a subset of the Cartesian product, S cross S. That is, R is a set containing ordered pairs from this set. This idea can be generalized to the idea of the relation from one set to another set. So these words, R is a relation from S to T, are used when S and T are both sets, and R is a subset of this Cartesian product, S cross T. That is, R is a set containing ordered pairs from S cross T. So ordered pairs of the form little s, comma, little t. There's some additional terminology. The set on the left, set S, is called the domain of the relation. The set on the right, set T, is called the range of the relation. Now realize that the earlier concept of binary relation on a set, that concept, is just a special case of a relation from one set to another set. So we can use the general term relation to mean relation from one set to another set, with the understanding that that term includes both kinds. It includes relations from one set S to a different set T. It also includes relations on a set S. Example 1. Let X be this set, capital A, B, D, E, denoting people, Ann, Bob, Dave, Edith, and let capital Y be this set, little c, p, s, I, denoting cake, pie, sorbet, ice cream. Define relation R from X to Y by saying that X tilde Y, or X is related to Y, means that person X ate dessert item Y at the picnic, with the set R defined explicitly by this set. So this ordered pair means that Anne had ice cream at the picnic. These two ordered pairs mean that Bob had cake and Bob had ice cream. Notice a few things about this relation. There's more than one pair of the form capital B, comma Y. That indicates that Bob had more than one item. Of course, Dave also had more than one item. Also notice that there's no pair of the form capital E, comma Y. That indicates that Edith did not have any dessert. Also notice that there's no pair of the form little x, comma S. That indicates that no one had sorbet. Let's go on. Now I want to talk about illustrating a relation from one set to another. Relations can take many forms, and so there is a variety of ways to illustrate them. It's always good to practice illustrating relations in different ways because in a given situation, one style of illustration may be more useful than another, so it's good to have practice knowing how to make lots of different kinds. When the domain and range are both finite sets, two common illustration types are the arrow diagram and the table. The convention for arrow diagrams is to put the domain on the left, and the convention for tables is to put the elements of the domain as the headings for the rows. So here are two illustrations for example 1. On the left in this drawing is a picture illustrating set capital X, and on the right in this drawing is a picture illustrating set capital Y. And each arrow in this drawing illustrates that a person had a particular dessert item. So for instance, this arrow that goes from capital A to little I, that illustrates the pair capital A, little I, in the relation that indicates that Anne had ice cream. In the table, the elements of the domain are the row headings, the elements of the range are the column headings, and you can see there's a dot in this cell corresponding to capital A, little I. That's the cell that illustrates that Anne had ice cream. Now I want to talk about the inverse relation. Every relation has an inverse relation. The symbol capital R superscript -1 is spoken R inverse, or the inverse relation for capital R. You can use this symbol anytime you have a relation R from a set capital S to a set capital T. What this symbol capital R superscript -1 means is the relation from set T to the set S. That is, R superscript -1 is a subscript of this Cartesian product, capital T cross capital S, defined this way. The set of ordered pairs in the relation capital R are the ordered pairs of this form. The ordered pairs little t, comma, little s, such that the ordered pair little s, comma, little t is an ordered pair in the relation capital R. In other words, the ordered pairs for relation capital R inverse are obtained by reversing the order of the elements in the ordered pairs for R. If we do that for our relation from example 1, we take all the ordered pairs from relation capital R, we reverse the order of the elements, and we get these new ordered pairs. Those are the ordered pairs for relation R inverse. Now, illustrating R inverse, we put its domain on the left. So its domain is capital Y. Its range we put on the right. Its range is capital X. Similarly for the table, the elements of the domain of capital R are the elements of set Y. They go on the left. The elements of the range of, this table should say capital R inverse. And the elements of the range of capital R inverse are the elements of set capital X. They go in as column headings. So notice this configuration of arrows looks different from the configuration of arrows that we had in the previous diagram. And the configuration of dots in the previous diagram looks different than the configuration of dots in the new diagram. Now finally, I want to talk about functions. This symbol, little f colon capital X arrow capital Y, is spoken, little f is a function from capital X to capital Y. What it means is this. What that symbol means is the following. Capital X and capital Y are sets, and little f is a relation from capital X to capital Y. So in other words, little f is a subset of that Cartesian product. And furthermore, it also means that little f has this extra property. For each x in the domain set, capital X, there exists exactly one little y in the range set, capital Y, such that this ordered pair, little x, comma, little y, is an element of the relation. This unique element, little y, that's an element of capital Y, is denoted by this symbol, little f parentheses x. So in other words, y equals f parentheses x. So this ordered pair, little x, comma, f of x, is an ordered pair in the relation. Now this meaning, all these words, can be expressed formally in very concise symbols. For every x in the domain, there exists a unique, that is, there exists exactly one, that exclamation point means exactly one, y in the range, such that y equals f, and this should be f of little x. Now, some more terminology. The set capital X is called the domain of the function little f, just like it was called the domain of the relation little f. And set capital Y is called the range of function little f. In our book, the range is sometimes denoted this way: the word range, parentheses, symbol f. Now, that particular element, y, which is f parentheses x, is called f of x. It's also called the value of f for the input x. It's also called the output of f at x. It's also called the image of x, or the image of x under the function f. So very peculiar terminology. Let's go back and look at example 1 again. Notice that that relation from example 1 is not qualified to be called a function because there's no output for the input E. That is, Edith did not have any dessert. Remember, the definition of a function is for each element of the domain, there has to exist exactly one element of the range such that this ordered pair is in the relation. If you go back up and look at example 1, there is no ordered pair with capital E on the left, but capital E is in the domain. And if you look at the arrow diagram, there is no arrow coming out of letter capital E. So there's no output that corresponds to the input capital E. So this relation, perfectly good relation from x to y, does not qualify to be called a function from x to y. Notice that the inverse relation, capital R inverse, is a perfectly good relation, but it's not qualified to be called a function either. Here's the relation capital R inverse. Notice for this relation, there's no arrow coming out of the letter little s. That indicates that nobody had sorbet. Now, as another example, consider this new function, defined by this formula, f of x equals x squared. For this function, the image of 2 is the number 4. That is, f parentheses 2 equals 4. You can illustrate this by an arrow diagram. You think of the function f as a machine. You illustrate it with this, what I would call a machine diagram. The input goes in on the left, and the output comes out on the right. You input x, and you get out x squared. So if you input the number 2, you get out the number 4. Example 3. Consider this equation, y equals x minus 2 over x minus 3. For most real numbers, that equation can be used to obtain a value of y. But for x equals 3, there is no corresponding value of y. Now, consider this proposed definition of a function. We would like to define a function, little f, from the real numbers to the real numbers, using that formula. Well, realize that that would not qualify as a function because x equals 3 is in the domain R, but f parentheses 3 does not exist. Mathematicians would say that this proposed function is not well defined. That means that that proposed definition fails some requirement that all functions must satisfy. Now consider this alternate proposed definition. Define a function called f with this as its domain, the set of all real numbers except 3, and this as its range, and use that same formula. Well, we see that this does qualify as a function because it satisfies all the requirements that a function must satisfy. That is, for every x in this set, this formula can be used to get a value of f of x in exactly one value. So this is a valid definition of a function. This is not a valid definition of a function. Let's go on. Example 4. A particularly simple function is what's called the identity function. The identity function on a set is denoted by this symbol. You write little I, little d, and then subscript a letter or some kind of symbol. It's spoken, the identity function, on S, or whatever symbol is sitting down here. When you write this symbol, the subscript is a symbol that represents a set. Now, what does this whole symbol mean? Well, it means a function. So that symbol represents a function. It's the function whose domain is the set S and whose range is the set S. Now, anytime somebody wants to sell you a function, they have to tell you the domain and the range, and they have to tell you how the function works. So here's how the function is defined to work. For every x that's in the domain, the corresponding output is this. The corresponding output is just the same as x. So in other words, if I do this, the identity function on the set of real numbers with 7 used as input, that means the output is going to be 7 as well. An arrow diagram for this, or a machine diagram, would be the following. And consider this example. If I use as input this messy expression, e to the minus sine theta, well, the output is going to be e to the minus sine theta as well. Whatever you feed in as input comes out as output. Let's go on. Now I want to talk about graphs of functions. A function whose domain and codomain are subsets of real numbers can be illustrated using a graph. But there are graphs that do not correspond to functions. The vertical line test articulates which graphs qualify to be graphs of functions. So the vertical line test for a graph to be the graph of a function is this. If for every little a in set capital A, the vertical line with equation x equals little a, if that vertical line intersects the graph exactly once, then the graph is the graph of a function with domain capital A. That is, the graph passes the vertical line test. On the other hand, if there exists an element little a in set capital A such that the vertical line with equation x equals a does not intersect the graph, or intersects the graph more than once, then the graph is not the graph of a function with domain A. That is, the graph fails the vertical line test. Let's go back and revisit example 2. Remember that example 2 was the function f of x equals x squared with domain the set capital R. Well, notice that every vertical line touches this graph exactly once. Here are some examples of vertical lines. This one on the left has line equation x equals -3. This vertical line on the right has line equation x equals 1. Each of those vertical lines touches the graph exactly once. Now let's go back and look at example 3. Consider this function, the function with domain, the set of real numbers except 3, and range, the set of real numbers, defined by this formula, f of x equals x minus 2 divided by x minus 3. Well, notice that every vertical line with equation x equals a, where a is not equal to 3, touches the graph exactly once. So for instance, here's the vertical line with equation x equals 5. Here's the vertical line with equation x equals minus 2. Notice that there is one vertical line that does not touch this graph at all. The vertical line x equals 3 does not touch that graph at all. But that's okay, because that x equals 3 is not in our domain. The domain is all real numbers except 3. Let's go on. For example 5, consider this equation, x squared plus y squared equals 1. The graph of this function is a circle, this circle shown. Some vertical lines touch this graph more than once. For instance, the vertical line x equals 1/2 looks like this, and it touches the graph at 2 places. So this graph is not the graph of a function. It is the graph of an equation, but it is not the graph of a function. So this equation cannot be used to define y as a function of x. Now I want to talk about the image of a set and the image of a function. In our definition of function, we considered the output of a function corresponding to a single input. That output was called the image of the input. So For instance, for the squaring function, we found that f parentheses 2 equals 4. That is, the image of 2 is the number 4. It's often helpful to consider the set of outputs that correspond to a whole set of inputs. That's the notion of what's called the image of a set. So this symbol, little f parentheses capital A, spoken f of a, or the image of a, or the image of a under the function f. Notice those are the same words we used earlier. We can use that symbol whenever we have a function, little f, from a set capital X to a set capital Y, whenever we have a function like that in the discussion, and whenever we have a set A that's a subset of the domain, capital X. And what this symbol means in this situation is it is the set of all outputs that result when elements of set A are used as inputs. That is, this symbol, little f parentheses capital A, when the thing inside is a whole set, it means a whole set of things of this form. F parentheses little a, where little a is an element, and that should say little a is an element of capital A. So you consider all of the elements from the set capital A, can call them little a, use each of them as inputs, and the corresponding outputs, the whole set of all those outputs, is called the image of the set capital A. So notice that that set, that image set, the image of the set A, is a set that lives in the range set capital Y. Because each of these outputs, all those outputs live in the set capital Y. Now there's a special case and some additional terminology. Notice that the entire domain X can be considered as a subset of itself. So the notion of the image of a whole set capital A includes the special case of the image of the whole domain capital X. In that special case, there's even more terminology. So I can use these words, the image of F, or this symbol, capital I little m parentheses F. What that means is this set F parentheses capital F. That means the set of all outputs that result when all of the elements of the domain set X are used as inputs. That is, this symbol, the image of F, or F parentheses capital X, those things mean the same thing, and they just mean the set of all possible outputs that you get from the function when you use elements of set capital X, the whole domain set, as inputs. Let's go back and revisit example 2 again. So in example 2, we have this function from the real numbers to the real numbers that's given by the formula f of x equals x squared. For this function, the image of this set is this set of outputs. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared is 0, and so on. If I consider this whole set, that's an interval, and consider the outputs that come from that whole set, the image is an interval as well. And if I use this interval, the set of all real numbers, as the input, then the corresponding image is also an interval. Now there are lots of different ways of writing this symbol. That same symbol can be written this way, F parentheses capital R, and that's for the symbol on the left. The symbol on the right can be written this way, the non-negative real numbers, the numbers greater than or equal to 0. We can also write this. This symbol stands for the image of the function f. So all three of these things denote the same thing. Notice that the range of f, way up here in this symbol, the range of f is the set of all real numbers, whereas the image of f is the set of non-negative real numbers. So the image of f is not equal to the range of f. Now I want to talk a little bit about the image and the range of a function. So the first remark is this: why is this thing, the range of the function, useful? isn't the image of f the more useful concept? So let's go back to the previous example. In this example, the range of the function was the set of all real numbers, but the only real numbers that could actually come out as outputs are the non-negative real numbers, the numbers greater than or equal to 0. The y values are always greater than or equal to 0. So we saw the image is not equal to the range. So not all real numbers are actually possible as outputs. Now it seems like we would be most interested in the actual y values that will be the outputs of a function. That is the image of the function. Why would we want to have this thing that's the range, that's larger than the image? Or put it another way, we could have just defined the squaring function differently. We could have said that the squaring function had the domain that's the set of all real numbers, and we could have just said its range is the non-negative real numbers. We could have used the same formula. Then in that case, the image would have been exactly the same as the range. Wouldn't we always want this? Well, the answer to this is a little subtle. Sometimes one does want to know exactly what the outputs will be that come out of a function. But sometimes you only need to know what kinds of outputs will come out. Sometimes both questions are easy to answer, but sometimes the first question is harder to answer than the second question. So let's go back to example 3. In example 3, we had this function given by this formula with domain being the set of all real numbers except 3, and the range being the set of real numbers. So it's easy to see that the output of this function will always be real numbers. But it's harder to see exactly what real numbers can actually be achieved as output. Now to find that out, we can find it out. We start with the equation, y equals x minus 2 over x minus 3. We solve that equation for x in terms of y. After some steps, you get this result, this new equation that says x equals 3y minus 2 over y minus 1. Now this equation has no solutions when y is equal to 1. That is, there are no x values that correspond to y equals 1. Well, that means that for the original function, there are no x values that will give a y value of 1. Now this sort of makes sense now. Notice that in this original function, the numerator and the denominator are not the same. For any value of x, the thing in the numerator is not going to be the same as the thing in the denominator. So that fraction, their ratio, will never equal the number 1. So we've determined that the image of f is the set of all real numbers except the number 1. The set of y values that can actually come out of this function is the set of all real numbers except the real number y equals 1. So notice that it was more difficult to determine the image than it was to determine the range. So sometimes, again, if you just care about what sorts of things are going to come out of the function, it's often easy to answer that. We could see right away that this function was going to produce real numbers as output. So it was easy to come up with a description of a range that would work. But it was much harder to come up with a description of the image. Now I want to talk about something that's a bit of a nuisance before we go on. Another remark about the image and range of a function. That is the different use of the terminology. Different books use the words image and range to mean different things. I'll compare our book to the book Discrete Mathematics by Susanna Epp that is often used here at Ohio University in Math 3050 and in CS 3000. In our book, the set of outputs that actually result from the inputs is called the image. And the set where those outputs live is called the range of the function. Now, in Susanna Epp's Discrete Mathematics book, the set of outputs that actually come out of the function is called the range. And the set where those outputs live is called the codomain. So you see that the word range gets used in a different way in the two books, And the word image gets used in one book and not the other, and the word codomain gets used in one book and not the other. So the takeaway from this is that there is no simple takeaway. Whenever you deal with these descriptions of the sets involving the outputs of a function, you have to be very careful about the terminology that you use and be aware that when you're reading something, you need to understand the terminology that the author was using. Now I want to talk about what's called preimage. Having learned about these concepts, the image of an element, the image of a set, and the inverse relation, we're equipped to understand the concept of preimage. So this symbol, f superscript -1 parentheses y, is spoken the preimage of y. You use this symbol when f is a function from some set capital X to some set capital Y. What this symbol means is the following. That symbol, the preimage of y, is defined to be the set of all inputs that will cause the output to equal y. Now, if it turns out that the preimage set is just a single element set, then it's often written without brackets. And also, the preimage of a whole set, if you consider a whole set in the range, then the preimage is defined the obvious way. The preimage of that set is the set of all inputs that will cause outputs to be in that set. Now that's a lot of words. Let's just do some examples. For our function f of x equals x squared, here are some preimages. The preimage of the single element 9 is this set. The preimage of 9 is a set containing two elements, x equals -3 and x equals 3, because both of those inputs cause an output of 9. The preimage of this single element y equals 0 is a set that contains just one element. The preimage of 0 is the set containing just 0, because x equals 0 is the only x value that causes y equals 0. So in that case, we can just write that the preimage is the number 0 instead of writing it as a set. But again, a lot of times, a preimage of an element can be a whole set containing more than one number. The preimage of this single element y equals -5 is the empty set, because there are no x values that will cause y to be -5. There is no x such that x squared equals -5, at least not in the set of real numbers. Now, the preimage of an interval can be an interval. So, for instance, the preimage of this interval is denoted this way, and it's this interval. On the other hand, the preimage of a whole interval can be just a single number. So, for instance, the preimage of this interval is denoted by this symbol, and it's just the number 0. The only x that causes a y value to come out in that interval is x equals 0. And the preimage of a whole interval can actually be the empty set. So consider this whole interval. The interval from -5 to 0 without the endpoints. So this symbol stands for the set of all x's that will cause y values that will come out in that set. Well, that's the empty set, because there are no x values that will cause y values in the interval from -5 to 0 without the endpoints. Observe that although the function from r to r defined by that formula is a function, this symbol f superscript -1 does not represent a function. For some single inputs like y equals 9, the output is a set containing two elements, -3 and +3, not just a single number. And for some inputs like the number y equals -5, the output is the empty set, not a number. So the symbol f superscript -1 does not represent a function in this case, but it does represent a relation from the real numbers to the real numbers. It's the inverse relation for for the original function, which is, this original function is a relation from R to R, and so this symbol represents the inverse relation. Remember earlier I said every relation has an inverse relation. Now in this case we've seen that symbol, that inverse relation, is not qualified to be called a function, but it is a relation from the real numbers to the real numbers. So again, in general, this symbol might not represent a function, but it will always represent a relation. But for some functions, this symbol does represent a function. In the next video, I'll discuss that, the criteria that will indicate when that's true. Now I want to talk about properties that functions may or may not have. Surjective, injective, bijective properties. These words, f is surjective or f is a surjection, are also spoken f is onto, but we won't use that terminology in our book. Those words are used when you have some function that you're discussing. What it means is for every element in the range, there exists an element of the domain, at least one, that can be used as input that will cause that element of the range to be output. What this means formally in terms of symbols is this. For every y value in the range, there exists an x value in the domain such that the output caused by that x value is the value y. In other words, for every element in the range, the number of elements in the domain that can be used to cause that element of the range to be output is greater than or equal to 1. There's at least one element in the domain that can be used that will cause that element of the range to be output. I wanted to say it this way because I want to write this expression here as the formal expression of what it means to be surjective. For all y's in the range, there exists at least one x in the domain such that the output caused by x will be y. Now, this is redundant. We don't really have to say the symbol at least one. When you write this, that really means there exists at least one. That's the convention. The second property that I want to talk about is the property of being injective. To say that a function f is injective means if two inputs cause outputs that are equal, then the inputs must be equal. That's written formally this way. For all x1 and x2, if the outputs are the same, then the inputs must have been the same. Now remember from discrete math that for every conditional statement there's a logically equivalent contrapositive statement. So the contrapositive is the following. If two inputs are not equal, then the outputs are not equal. So remember that the contrapositive is the following. The contrapositive is you reverse the order of P and Q and you put negations on both of them. So the contrapositive written formally is this. For all x1 and x2 in set capital X, if x1 is not equal to x2, then f of x1 is not equal to f of x2. Another wording of the injective function definition is this. For every element in the range, there exists at most one element of the domain that can be used as input to cause that element of the range to be output. This alternate wording does not imply that there are any elements that will work. It just says that there cannot be more than one. Writing formally, we could write this. For all y's in the range, set capital Y, there exists at most one x in the domain set such that that x will cause that y to be output. And we could write this a different way as well. We could say that for every element in the range, the number of elements in the domain that can be used as input to cause that element of the range to be output is some number n that's less than or equal to 1. Well, that means that n is equal to 0 or n is equal to 1. Now, we're often interested in determining whether or not a particular function has either of those properties above, the injective property and the surjective property. That's why it's going to be useful to know the negations of those statements. To negate this statement F is surjective, it's helpful to use the formal presentation of that. So the statement that F is not surjective is obtained by just parking the negation symbol in front of that expression. And then we discussed this in previous videos. You simplify this, you make it clearer by moving the negation as far to the right as possible. Notice that when the negation moves past that universal quantifier, it becomes an existential quantifier. And when the negation moves past this existential quantifier, it becomes a universal quantifier. We end up with this new symbolic expression that says F is not surjective. There exists a Y in the range set such that for all X in the domain set, the output caused by X is not equal to Y. So there is an element in the range such that no element of the domain can be used as input to cause that desired element of the range to be the output. Similarly, to find the negation of the statement of injective, we use this formal expression for injective. We put that whole formal expression here, and we park the not in front of it. So to say that F is not injective means not all this junk. And then we get to work moving the not to the right, one step at a time. And we end up with this. To say that F is not injective means there exist two inputs that are not equal, but that cause the same output. There's another way of saying that F is injective, though. There's the contrapositive statement. Remember this one? For all pairs of inputs, if the inputs are not equal, then the outputs are not equal. It would be interesting to try negating that and see what we get. Well, if we negate that expression for the statement of F being injective, what's really cool is if we put the negation in front and we simplify it, oops, we end up with this, which is exactly what we ended up with in the previous page. So even though there are two different ways of expressing the idea that F is injective, there's this original conditional statement, and there's this contrapositive conditional statement. If I take the negation of either one of them, I end up with the same thing. There exist two inputs that are not equal, but that cause the same output. So that's really cool, that the negation of the contrapositive statement is exactly the same as the negation of the original statement. And that makes sense because remember, the contrapositive statement is logically equivalent to the original statement. Now, there's another wording of injective. This. For every element in the range, the number of elements in the domain that can be used as input to cause that element of the range to be output, the number of such inputs is n, which is less than or equal to 1. Well, that's what it means for F to be injective. To say that F is not injective means this. There exists an element in the range such that the number of elements in the domain that can be used as input to cause that element of the range to be output is n greater than 1. So the negation of n less than or equal to 1 is n greater than 1. In other words, there exists an element in the range such that more than one element of the domain can be used as input that will cause the element of the range to be output. So we've articulated a couple of different ways now of wording the statement that a function f is not injective. We'll see that both can be useful in different situations. So for instance, which of these functions is surjective and which is injective? Well, for surjective, notice that this function does not have any arrows pointing at the letter P. The letter P will never be output, so this is not surjective. Look at this map, or this function. R and T never come out as outputs. On the other hand, this function has the property that every element of the range, P, Q, R, those are all obtained as outputs. And same for this function. All of the elements of the range can be achieved as outputs. But this function is not surjective. And this function is not surjective. Now let's consider injective. Are there any cases where two inputs cause the same output? And there are. Those two inputs cause the same output. How about this function? Well, there are no two inputs that cause the same output, so this function is injective. What about this function? Notice that these two inputs cause the same output, and these two inputs cause the same output. So this function is not injective. What about this function? Notice that any two inputs that are different cause outputs that are different. So this function is injective. Now look at this function. These two inputs cause the same output, so this is not injective. And finally, this function is not injective. Let's go on. Now I want to talk about graphs of surjective and injective functions. For a function whose domain and codomain are sets of real numbers, then the surjective and injective properties have corresponding behaviors in the graph of the function. They're articulated by what are called the horizontal line tests for surjectivity and injectivity. So suppose that some set capital A is a subset of real numbers, and some set capital B is also a subset of real numbers. And suppose that function f has domain set capital A and range set capital B. The surjectivity property of f relates to the behavior of the graph of f in this way. To say that f is surjective means that for every horizontal line of the form y equals b, where b is an element of capital B, every line intersects the graph of f at least once. That is, f passes this horizontal line test. If f is not surjective, to say that f is not surjective means that there exists a horizontal line of the form y equals b, where b is some element of capital B. There exists some horizontal line of that form that does not intersect the graph at all. Now what about injectivity behavior? To say that f is injective means this. For every horizontal line of the form y equals b, where little b is an element of capital B, that horizontal line intersects the graph of f at most once. We say that f passes the horizontal line test. But to say that f is not injective, well, that means that there exists a horizontal line, y equals b, where b is in capital B, such that that horizontal line intersects the graph more than once. So for instance, let's look at the graph of the function f of x equals x squared. Notice that this horizontal line does not intersect the graph at all. So we suspect that f is not surjective, or this illustrates that f is not surjective. And look at this horizontal line. So f is not injective either. Now write a formal proof of the claims. Well, that is, we have to refer to the official definition. So remember what it means for a function to not be surjective. To say that a function is not surjective means that there exists an element in the range such that no element of the domain can be used as input that will cause that output. So to prove that some function is not surjective, we have to come up with an example. So the proof would be this. Let y equal -1. Then there is no x such that f of x equals -1. So that's the end of the proof. Now how do we prove that f is not injective? Well, let's go back up and see what the statement of not injective means. The negation of injective is this. there exist two inputs that are not equal, but that cause the same output. So if we want to prove that the function is not injective, we have to address that. So we have to say this. We have to come up with an example. We could write this way. So we point out that there exist two inputs that are not the same, but that cause outputs that are the same. So again, the illustrations are good for understanding injectivity or not injectivity, and surjectivity or not surjectivity. But for an actual proof, you have to reference the definitions. Now consider this function, f with this domain, the set of all real numbers except 3, and this range, the set of all real numbers, defined by this formula. Using this graph, explain what surjective and injective properties you think the function has. Well, notice that this horizontal line, y equals 1, does not touch the graph. But y equals 1 is in the range. And so we have failed that horizontal line test for surjectivity. What about injectivity? Well, notice that there are no horizontal lines that touch the graph more than once. So we've passed the horizontal line test for injectivity. So f is injective. But now how do we prove this? How do we prove that f is not surjective? Well, let's let y equal 1. Notice that that is not in the image of f. So f is not surjective. There is no x value that will cause y equals 1 to come out. Now, we can see that the function f is injective. Now, how do we prove that? For that, we have to go back up and look at the definition of injectivity again. To say that f is injective means this universal statement and this universal statement. So if we want to prove that f is injective, we have to use those statements in our proof. Now, this statement of injective is of the form of a universal conditional statement. So our proof is going to be a direct proof. We're going to introduce generic elements of the domain that satisfy the hypothesis, and then we have to show that they satisfy the conclusion. So we're going to say, suppose that x1 and x2 are in the set of the domain, and suppose also that f of x1 equals f of x2. And we have to get to this statement we have to show that therefore x1 equals, we have to show that x1 equals x2. Well, how do we do that? Well, let's consider the equation. So the original equation for the function y equals x minus 2 over x minus 3 can be solved for x in terms of y. So if we know the value of y, we can find out the value of x. Well, notice that for the first x1, we know the value of y is f of x1. So let's use that. x1 is going to be 3 times f of x1 minus 2 over f of x1 minus 1. But wait a second, that's going to be the same as 3 times f of x2 minus 2 over f of x2 minus 1. And that's because f of x1 is known to equal f of x2. But wait a second. What we've got here is just the expression for x1. So what we've proven is that, sorry, this should be x2. So we've shown that if f of x1 equals f of x2, then x1 equals x2. So we've proven injectivity using the definition of injective. Now consider this function, f of x given by this cubic polynomial. Using this graph of the function, figure out what surjective and injective properties you think the function has. Well, notice that every horizontal line touches the graph exactly once. So we can see that f is both surjective and injective. Now we have to write a formal proof of that. Here's the function, x cubed minus 3x squared plus 3x plus 1. So how do we prove that? Well, notice that f can be rewritten. So f of x equals x cubed minus 3x squared plus 3x plus 1. That is actually x cubed minus 3x squared plus 3x. So this is a trick, being able to do that. And what that is x minus 1 cubed plus 2. So you can see that this graph is a standard cubic graph that's been moved over to the right 2 units and up 1 unit. So we can think of this as an equation, and we can solve for x. So that is the equation for x in terms of y. That tells us that no matter what the value of y is, we can find the value of x that will work. We use this equation. And that also tells us that if two x values cause the same value of y, then those x values must have been the same x value, because this equation would give the same x value. So the fact that we are able to solve the equation for x in terms of y tells us that the function is both injective and surjective. All right, let's go on. In this example, we're going to consider another cubic polynomial, and I want to use the graph to figure out what surjective and injective properties we think f has. Well, notice that every horizontal line touches the graph at least once. So f is surjective. On the other hand, notice that some horizontal lines touch the graph more than once. So we pass one horizontal line test, the test for surjectivity, but we flunk the other horizontal line test, the test for injectivity. Now, write a formal proof of the claims that we made in A. Well, I'm not going to do this completely, but I'm going to point out that this equation, or this function, x cubed minus 6x squared plus 11x minus 6, can be factored. So the factored form makes it easy to see the x-intercepts. So we can just pick two of those. So notice that x equals 1 is not the same as x equals 2, but f of 1 equals f of 2. So not injective. To see that the function is surjective is a little bit harder. I think I'm going to skip this. The way to think of it is the end behavior. One end goes up, the other end goes down, and the graph has no breaks or jumps in it, so that means that every y value is going to be crossed by that function. But I'm going to skip that. I want to finish. Let's go on. Finally, I want to talk about bijective functions. To say that a function is bijective, in some books this phrase is used, one-to-one correspondence. means that the function is both injective and surjective. In some books, they would say f is both one-to-one and onto. We're not going to use that terminology. We're going to use injective and surjective. It means that for every element in the range, there is exactly one element of the domain that can be used as input to cause that element of the range to be output. So written formally is this: for every element of the range, there exists exactly one element of the domain such that that input causes that y value to be output. Now, I won't go back and revisit our earlier examples to see which ones are bijective. You get the idea. Whichever ones are both surjective and injective are bijective. And finally, let's remember that this function that we talked about earlier, with domain the set of all real numbers except 3, and the range the set of all real numbers, was injective, but it was not surjective. But remember that we can use the same formula to define a new function. We can use the same domain, the set of all real numbers except 3, and use a different range, the set of all y values except 1, and use the same formula. Then in that case, the function is surjective. Every horizontal line of the form y equals b, where b is not equal to 1, does touch the graph exactly once. Those are horizontal lines corresponding to y values in the range set are not equal to 1. Now there is a horizontal line that doesn't touch the graph, but that's okay. I'm going to do that I'm going to draw that one in yellow. This line, y equals 1, does not touch the graph, but that's okay because y equals 1 is not in the range set. That's the end of the example, and that's the end of the video. Thank you.